In the world of traditional programming, functions reign supreme. They are the workhorses, the building blocks of any program. Think of a function as a well-defined recipe. It takes in specific ingredients, follows a set of instructions, and produces a predictable dish. Let's say we have a function that calculates the area of a rectangle. We provide the length and width as inputs. The function performs a simple multiplication, length times width. It then presents us with the calculated area as the output, elegant in its simplicity and reliability. This predictability is a cornerstone of traditional programming. Given the same inputs, a function will always yield the same output. This deterministic nature is essential for building software where precision and consistency are paramount. However, the world is rarely as straightforward as calculating the area of a rectangle. What happens when the problems we want to solve become more complex, more nuanced? That's where machine learning algorithms step in, offering a fundamentally different approach. Machine learning algorithms, unlike their function counterparts, are not explicitly programmed with a fixed set of rules. Instead of being given a recipe, they are given a cookbook and a set of successful dishes. Imagine providing an algorithm with countless images of cats and dogs, each labeled accordingly. The algorithm's task is to learn from these examples, identifying the patterns and features that distinguish a cat from a dog. It's like trying to reverse engineer a recipe by tasting the final dish. This learning process is at the heart of machine learning. Algorithms use statistical methods to analyze and understand the data. They identify correlations, patterns, and relationships that wouldn't be apparent to the human eye. Through this analysis, they build a model, a representation of the knowledge gleaned from the data. This model, once trained, can then be used to make predictions on new, unseen data. Show it a picture of a furry creature and it will, based on its training, predict whether it's looking at a cat or a dog. This ability to generalize, to apply learned knowledge to new situations, is what makes machine learning so powerful. The fundamental difference between traditional functions and machine learning algorithms lies in their purpose. Functions are task-oriented. They perform specific computations like calculating the area of a rectangle or sorting a list. Machine learning algorithms, however, uncover hidden patterns and extract insights from data. They make predictions or decisions based on these insights. For example, a machine learning algorithm can identify spam emails by learning sophisticated patterns. This adaptability makes machine learning ideal for complex, dynamic problems. The nature of inputs and outputs further distinguishes functions from machine learning algorithms. Functions typically work with structured data. Think numbers, strings, or arrays data types that fit neatly into predefined categories. The output of a function is directly determined by these inputs and the function's internal logic. Machine learning algorithms, however, often deal with raw, unstructured data images, text, audio, or sensor readings. They don't simply process this data, they learn from it. They extract meaningful features, identifying the signal within the noise. Consider an algorithm designed to recognize handwritten digits. The input is an image, a collection of pixels. The algorithm doesn't see the image as a human does. Instead, it identifies features, the shapes, curves, and edges that differentiate a 7 from a 1 or a 3. These features are then used to train the model, enabling it to make predictions on new, unseen, handwritten digits. The output of a machine learning algorithm is not a direct result of a computation. It's a prediction, a probability, or a classification based on the patterns learned from the data. This distinction highlights the move away from explicit programming towards a more data-driven approach. Section 5. Complexity, straightforward logic versus intricate networks. Functions in their essence are relatively simple structures. They encapsulate a set of instructions executed in a predetermined order. Their logic is transparent, their behavior predictable. Even complex functions can be broken down into smaller, more manageable modules. Machine learning algorithms, especially deep learning models, can be significantly more complex. They often involve intricate networks of interconnected nodes, each performing simple operations but collectively exhibiting emergent behavior. These networks are not explicitly programmed, they are shaped by the data they are trained on. This complexity can make understanding and interpreting machine learning models challenging. We can't simply trace the flow of execution as we would with a function. Instead, we rely on techniques to visualize the model's internal representations to understand which features are most influential in its decision-making process. This complexity, however, is also the source of machine learning's power. It allows algorithms to model intricate relationships within data, to capture nuances that would be impossible to represent with handcrafted rules. It's this ability to navigate complexity that allows machine learning to tackle problems previously considered intractable for traditional programming approaches. Section 6. Optimization, efficiency and execution versus model refinement. Optimization in traditional programming focuses on code execution efficiency. We minimize operations, reduce memory usage, and optimize algorithms for speed. The goal is fast, efficient code on given hardware. In machine learning, optimization means refining model accuracy and generalizability. We fine-tune parameters for the best performance on tasks. This involves training on large datasets and validating performance. The goal is a model that generalizes well to new data, ensuring models are robust, reliable, and applicable to real-world scenarios. Section 7. Data handling, structured inputs versus feature extraction. Traditional functions excel at processing structured data, neatly organized information that conforms to predefined formats. Think databases with rows and columns, spreadsheets with cells and values, or comma-separated files with clearly defined fields. Functions can easily access, manipulate, and transform this structured data. Machine learning algorithms, however, often grapple with unstructured data, the messy, real-world information that doesn't fit neatly into predefined categories. Think text documents, images, audio recordings, or sensor readings. These data sources are rich in information, but require a different approach to handling. Machine learning relies heavily on feature extraction, the process of transforming raw, unstructured data into a format that algorithms can understand. This might involve converting text documents into numerical representations of words, extracting edges and shapes from images, or identifying patterns in time series data. This ability to handle and extract meaningful information from unstructured data is a key strength of machine learning. It opens up a world of possibilities, allowing us to apply these techniques to problems that were previously difficult or impossible to address with traditional programming approaches. Section 8. Abstract concepts versus compiled code algorithms as blueprints. In traditional programming, we write code, a set of instructions that a computer can understand and execute. This code is then compiled into machine-readable instructions, specific to the target hardware architecture. The compiled code is what actually runs on the machine, performing the desired computations. Machine learning algorithms, at their core, are not compiled code. They are abstract concepts, mathematical formulations, or blueprints for learning from data. These algorithms are implemented in code, but the code itself is not the algorithm. It's the instantiation, the concrete realization of the abstract concept. Think of an algorithm like the design for a house. The design itself is not the house, it's the plan, the blueprint for building the house. Similarly, a machine learning algorithm is a blueprint for creating a model, a set of instructions for learning from data. This distinction is subtle but important. It highlights the conceptual nature of machine learning, the focus on the underlying principles of learning and inference rather than the specific implementation details. It's this abstraction that allows for the development of general-purpose learning algorithms that can be applied to a wide range of problems. Section 9. A paradigm shift, from rules to data-driven intelligence. The emergence of machine learning represents a fundamental shift in how we approach problem-solving with computers. Traditional programming relies on explicit rules and instructions, a deterministic approach where we tell the computer exactly what to do. Machine learning, on the other hand, embraces a data-driven paradigm. We provide the computer with data, and it learns the rules, patterns, and relationships from the data itself. This shift from rules to data has profound implications. It allows us to tackle problems that were previously too complex, too nuanced, or too data-intensive for traditional programming approaches. Machine learning is not a replacement for traditional programming. It's a complementary approach, a powerful new tool in our problem-solving arsenal. As we generate ever-increasing amounts of data, the importance of machine learning will only continue to grow. It's a field with the potential to revolutionize industries, accelerate scientific discovery, and enhance our lives in countless ways. By understanding the fundamental differences between traditional functions and machine learning algorithms, we can better appreciate the power and potential of this transformative technology.